As we learned previously, analysis of variance, or ANOVA, is a statistical technique used to test whether the means of three or more groups are significantly different from each other. And we have discussed the example of ANOVA a few times now. Does mean diastolic blood pressure differ significantly across these three groups: underweight group, normal weight group, and overweight group?
In t-test, when we had only two values, we can subtract them easily. For example, say if we have two groups, males and females have, say, mean diastolic blood pressure of 84.5 millimeters of mercury, and males have mean diastolic blood pressure of say 86 millimeters of mercury, right? So now we can easily see 86 minus 84.5 equals 1.5. So we can right away say that females have 1.5 millimeters of mercury uh, mean diastolic blood pressure lower than that of males. And the formula to calculate the confidence interval was again very simple. Say we get a difference of the range in the difference be 1.2 to 1.7. Now this confidence interval is it does not contain zero, so it is easy to say that the difference between male and female as in terms of their diastolic blood pressure is statistically significant. But if you have three groups, like here, you have overweight individuals, normal weight individuals, and underweight individuals. Now, say overweight individuals have mean diastolic blood pressure of say 90, and normal weight individuals have diastolic blood pressure of say 80, and underweight individuals have mean diastolic blood pressure of say 75. I'm just throwing some values just for example. But now the thing is that, are they statistically significantly different? We cannot really make out here because there are three values, not two, and the resulting values can be between these two and these two and these two, right? So in that case, analysis of variance is a better test for such kind of a scenario. Analyzing variances is a quite simple process. You calculate the total variability, which is in turn calculated from the variability within groups and the variability between groups. The total variability is also called total sum of squares, or SST, because of the process which is used to calculate total variability. And variability between groups is also called model sum of squares. And finally, variability within groups is also called error sum of squares. And the total variability is calculated by adding the model sum of squares and error sum of squares. Let's try to understand the calculation of ANOVA by this simple example: pain scores by sex. Do migraine-related pain scores differ between males and females? And then the measurement would be the self-reported pain on the scale of 1 to 10. These are still two groups, males and females, but this calculation can be extended to 3 groups, 4 groups, or 5 groups, but we'll use two groups because it is easier to understand the underlying calculations. So in this example, our exposure of interest would be males and females, and our outcome of interest are the pain scores. Now let's plot the values, the supposed values for our participants, and then we will calculate the variance between groups and within groups. Okay, suppose we have only 6 participants in our study, 3 males and 3 females. First male scored his pain to be 7 out of 10. Second male 8, third male 9. The first female scored her pain as 3, second female as 4, and third female as 5. In the first step, we will calculate the overall mean for all the participants in our study. So that would be 3 plus 4 plus 5 over here, 7 plus 8 plus 9 divided by 6. And if we sum these values up and divide them by 6, the answer would be 6. So the overall mean for all the participants in the study is 6. In the second step, we calculate the mean separately for both our groups or all our groups. For example, the mean pain score for the males would be 7 plus 8 plus 9 divided by 3, which comes down to be 8. Okay. Similarly, for the females, the value will be 3 plus 4 plus 5 divided by 3, which comes out to be 4. So 4 is the average score reported by the females. Now we can simply calculate the between group variability, which would be the average difference of each group from the total average. For example, in case of males, the average for male was 8, and the average for the overall cohort was 6. So the difference for the male group will be 8 minus 6. And for the females over here, we see that the average pain score for the female was 4, and the difference from the average of the overall cohort 6 would be 4 minus 6. And now to calculate the between group variability for the male, we're going to square it up, because otherwise the negative signs will mess up our calculation. So we will square 8 minus 6, and then we're going to multiply it with the total number of participants in our study, which comes down to be 3 times 4, because 2 square is 4, and 3 times 4 is 12. And the between group variability for the females is 4 minus 6 square, which is in fact minus 2 square, which comes down to 4. So the total variability within female group is 3 times 4, because there were 3 participants there. So 3 times 4 is 12. Now, the between group variability, this is simply the sum of the variability in male group and that of female group, which is 12 plus 12 is equal to 24. So our SSM, or model sum of squares, or between group variability, all of them are the same, is 24. In step 3, then we calculate the within group variability, which is a simple calculation. For example, we calculate the within group variability for females as 3 minus 4, because the first person has scored her pain as 3, and the average for the whole group was 4. So the difference for the first person was 3 minus 4. The second person was right on the average. She scored 4, her pain score as 4, which is at the average for that group. And the third person, third female, she scored her pain as 5, so it will be 5 minus 4. And among males, the first male scored his pain as 7, so the difference is 7 minus the average for the male, which is 8. The second person scored his pain as 8, which is at the average for the male group, and the the last male, the third male scored his pain as 9, which is a difference from the average by 1, 9 minus 8. And when we are calculating with total within group variability, it will be 3 minus 4 square. We square them to get rid of the negative signs if there are any, the old school method. The second person, 4 minus 4 square. Third person, third female, 5 minus 4 square. First male, 7 minus 8 square. Then second male, 8 minus 8 square, 9 minus 8 square. And if you calculate all these numbers, the total within group variability will be will come down to be 4. Now the total variability is simply the addition of the between group variability, that is sum of square, model sum of squares, and within group variability, or error sum of squares. So it comes down to be 24 plus 4 equals 28. R square is a very important concept, and you must understand it fully. You can rewind this video or watch it as many times as you can, but this is a very commonly used value in science, and is highly critical to evaluate any relationship between an exposure and an interest and an outcome. Basically, it represents the portion of variability explained by the exposure. Okay, I will repeat again. It represents the portion of variability which is explained by the exposure. In this case, it was sex. It is calculated by dividing the between group variability, SSM, by the total variability, SST. We have just calculated that between group variability, that was the difference in the pain scores between males and females, which comes down to be 24. And we know that the total variability in our sample was 28. So if we divide 24 by 28, we get 0.857, which is like 85.7%. So the interpretation would be that in our cohort of those 6 individuals, 3 females and 3 males, 85.7% of the total variability in pain scores is explained by the group differences. So again, I cannot emphasize enough how important R square is. We'll be using this this value again and again, even in linear logistic regressions. The calculation of F statistics is pretty simple, but the concept behind it is way more important. And the calculations is simply between group variability divided by within group variability. But the concept is that, for example, if I mean, there will always be some variability as we collect data, right? So somebody will have a diastolic blood pressure of 86, 84, 83, or the weight of say 150 pounds, 140 pounds, and 200 pounds, or whatever. So there will always be variability within the groups, right? But if the variability between the groups is high, for example, the average difference of the mean diastolic blood pressure of males is say 20 millimeters higher than the average, and for the females it is 10 millimeters lower than average of all, then it makes a huge difference. That means that sex is having a role in determining the diastolic blood pressure. And same goes with more than 3 groups. For example, if we are comparing the diastolic blood pressure between overweight individuals, normal weight individuals, and underweight individuals, and we see that between group variability is higher, much higher than that of within group variability. Of course, those who are underweight, they will have variability of, say, diastolic blood pressure among themselves, and same goes with the other two groups, overweight individuals and normal weight individuals. So it is in fact the ratio of how much is the variability between these groups, overweight, normal weight, underweight individuals, or male or female sex groups, and within the group, which is error sum of squares. So if there is a high F, which means that the group means differ more than expected by chance. But if the difference between these two groups is low, you will have low F stats, which means that the difference might be due to the random variability. Let's calculate these values and then you will understand this concept more. So the calculation for F statistics is pretty simple. You divide the model sum of squares, that is the between group variability, with that of error sum of squares, which is the within group variability. But you do divide each of these values by the degrees of freedom to factor in the total number of values you have in each of these groups. For example, in within group variability, we have two groups. So with the concept of degrees of freedom that we covered in chapter 4, the value for degrees of freedom will be 2 minus 1. And the error sum of squares, we had 6 participants there and 2 groups. So the degrees of freedom will be 6 minus 2, that would be 4. Let's calculate and I will explain it again. Okay, so the DF stands for degrees of freedom, and DF1 here, which is degrees of freedom 1, that is between the groups, and we know that we have only 2 groups, male and female. So K is the number of groups minus 1 by because we know that the last value we are not able to modify. That is the concept of degrees of freedom. So it will be 2 minus 1, which is 1, and degrees of freedom 2 here is within the group degrees of freedom. We know that we had 16 individuals in our study, and n is the total number of sample n is the total number of sample, which is the 6 individuals, and k is the number of groups too. So the total degrees of freedom we have here is 4. So now let's calculate the F statistics. We know that between group variability we calculated previously was 24. We divide them by the degrees of freedom between group, which is 1. And for the within group variability, error sum of squares, we calculated it to be 4, and we're going to divide it by 4 again, which is the degrees of freedom here. And once we have summed these ones up, we have calculated these values up, we will get 24 over 1, which is 24. So the interpretation of this value 24 is that this means that the variance between groups 24 is 24 times greater than the variance within group 1. So between group difference was 24 times higher than within group, right? Indicating that there is a statistically significant difference between the group means. In summary, analysis of variance, or ANOVA, helps us test the statistically significant differences between more than 2 group means, right? And it separates the variability into between group and within group components. These values, R square and F statistics, help quantify the strength. So R square helps quantify the strength, and F statistics helps in quantifying the significance of the group effect. This method is very widely used in health research when comparing multiple exposure levels or categories. See you in the next lecture.